Hello fellow problem solvers, so today we're going to be doing IMO 2022 problem number 6, the hardest problem of the IMO, a combinatorics, a beautiful one at that, and I suggest you try it out for at least half an hour, actually at least 45 minutes, ideally somewhere between 90 to even 150 minutes. I'd even do 180 minutes on this one, not more than 4.5 hours. If you'd like to go along with us, read through the problem and put your first ideas out on paper for the next 15 minutes. 15 minutes, and now without further ado, let us begin. So what do we have in the problem when we first read through the problem? Okay, we have this Nordic square. Okay, it's going to have numbers. We're going to have an n times n square. Say for 3, we're going to have a square with numbers 1, 2, 3, 4, say 5, 6, 7, 8, 9. And then we need to calculate the number of paths. Uphill paths, okay, we have these values. These are numbers which have only numbers that are, what's it called, higher than them. So 1 is a valley, 5 here is a valley, 4, 9, 7, 8 isn't a valley, 2 isn't, 3 isn't, 4 is not. And these seem to be like the values. Okay, we have 2 values. And a path starts, it contains at least one cell. Okay, so the first cell is a value, so this is a path, just put 1 on it. I think with just a 5 on it is a path. Then what do we have? We have that every subsequent cell of the valley is its neighbor. Okay, so we can go from 1 to 2, 7, 6, or 9. And that the numbers written in this are in increasing order. Okay, so if we go from 1 to 2 and from 2 to 8, we can't now go to a 7. But we could also just go from 1 to 2, stop there. And we must calculate the number of smallest possible uphill paths in a Nordic square. Okay, so what do we do when we are just starting the problem, don't know what to do with it? What is this heuristic that I keep mentioning over and over again? That is to play around with the problem. So if you haven't done that in these 15 minutes, please, what are you waiting for? Play around. Let's play around for n equals 2, 3, and see what is happening. And now let us play. So for n equals 2, let's see how many uphill paths we could have. So we're going to, we can say, okay, 1 is here, and now 2 is either going to be here or here. Like these two are symmetric. So if a 2 is, say, here, then 3 and 4, it doesn't matter what they are, say they're here and here. And now let's count the number of uphill paths. Okay, so one path is with a 1, another one is with a 2. And then we have a 1, 3, a 1, 4, a 2, 3, a 2, 4. So a total of 6 paths if we do it like this. Okay, let's do it again. Let's see what happens if we put 2 next to 1. Okay, now we can have, say, a 3 and a 4 here. Now we have paths 1, 1, 2, 1, 2, 3, 1, 2, 3, 4. Okay, this is smaller than that, so we can get 4. And now here, what do we have? Say 1, 2, 4, 3. I can go, I can also go from 1 to 4. I forgot about that path over here. So I have 5, again smaller than this one, but I can't go from 4 to 3. So here I can go 1, 1, 2, 1, 2, 4, 1, 3, and 1, 3, 4. So these are all the possibilities. They'll give me a 5 as my minimum. Okay. Is there any way we could prove that we can't? Like, why do we have 5 here as opposed to 6 here? Well, one thing is, here we had multiple uphill paths. And like when I'm at any number, I can choose between 3 and 4. Here, I'm always going to go from 3 to 4, from 2 to 3, from 1 to 2, and I can go from 1 to 4. So there are these sorts of, like potential paths. Like every single one of these 2 neighboring cells, there is but that gives me like where I'm allowed to go. And here, actually it goes this way. And here it seems the trick was, I don't know, maybe the main difference is we have 2 paths, 2 valleys. Maybe it's the fact that we just need, 1 valley. Maybe that's a solution. Well, how do we check that out? Well, n equals 2, that's not really a lot of play. For n equals 1, there's 1 path. For n equals 2, there's 5 at a minimum. So we have a 1, a 5. Let's see what else is happening. What's happening for n equals 3? This could be an interesting problem, like how many what even makes these paths paths? You know, n equals 3 is maybe a much nicer thing for us to play with. So let us say 1, 2, 3, 4, 5, 6, 7, 8, 9. I just made this a thing, you know. So let's see how many paths. 1 to 2, 2 to 3, 3 to 4, 5, 6, 7, 8, and a 9. Okay. I could also go from 6 to 9. I could go from 1 to 8. I go from 2 to 9. I can go from 4 to 9, 6 to 9. And now how many paths? So I have 1. Like this seems to be my only value, right? So I think I should maybe, you know, have a minimum here. But we should always, you know, try to see, why is that a minimum? How can we show it's a minimum? So we have 1, 1, 2, all the way till 1, 2 to 9. And that gives me 9 possibilities. Plus, I could go from 1 to 8, right? 1, 8, and then 1, 8, 9, these paths. So 1, 8, 1, 8, 9. And then I could go from 1 to 9. I could go 1, 2, 3, 4, 9. 1, 2, 3, 4, 5, 6, 9. And that seems about it. So I have 9 plus 2 plus 3. So I have 14 total paths that I can go if I just go like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's about one value. Now, maybe a hypothesis would be, okay, if there's just one path, does that mean there's going to be just, if there's just one value, does that mean if we have one value that we're only going to have one path? You know, that's maybe a hypothesis that just forms from playing around with this. So let's, you know, do more tables with 3 numbers. Please pause, do that, try it out. I'm going to write it up here and clean this up. And what turns out is our hypothesis is false by playing around. Our hypothesis that, oh, one value means the minimum number of paths. No, I have 13 paths here, and here I have 21 paths. Just one value, different constructions. And you get this through playing around with different constructions. And the big question is, why is this 13 paths? Why is this 14? But why is this 21? Why did I explode in the number of paths but still remain the same in the number of values? And can I find a minimum? Is this my actual minimum? When I'm playing around, it seems to be, and I have 1, 5, 13. What is happening? Why am I having the uphill paths here? Like, how many paths will I have? And is there a way I can guess a solution? Is like there pairs of stuff that's happening? We're gonna have n squared numbers. Maybe that's something to do with n cubed into the power of 4. Maybe that's what's happening here. I mean, but then there's like neighbors, sure, there's n rows and columns. How many, like say, neighborhoods, these edged relationships, really, if we're thinking about paths, how many edges are there? Well, n rows, like somewhere around 2 times. So we have, for each row, we have n minus 1 edges here, so times n, so that's n times n minus 1, n over here, n minus 1 times n over here, so a total of 2 times n minus 1. Like, what is that for 1 and so for 1 and 2? That gives us, what's it called? N equals 2 would give us 4. Here would give us a 12. Here would give us a 0. So, I mean, maybe it's something to do with that. Okay, maybe it's like that's what the solution is like. Maybe too soon to be able to tell right away. But it seems there's something like, where are these new paths coming from for here? Why do we have so many paths? Is it the fact that they are circular here, they're not circular there? And if you play around, you might see, wait a second, if I just construct 1, 2, 3, and then it goes, say, 4, 5, 6, 7, and actually no. If you construct not that, but actually construct this, it goes 1, 2, 3, 4, 5, 6, 7, 8, 9. What you get is you also get 13 paths. Just, look at it. This is the only what's it called, valley that we have in here, and the number of paths is I have 1, I have 1, 2, I have 1, 9. These are my length 2 paths. I have 1, 2, 7, 1, 2, 3, and then I have 1, 2, 3, 4, and 1, 2, 3, 5. From there I get 1, 2, 3, 4, 8. I get 1, 2, 3, 5, 8. 1, 2, 3, 5, 6. As well, this one, here we go. And I forgot a 1, 2, 3, 9, 1, 2, 3, 9. And from here I also have this one, 1, 2, 3, 5, 6, 9. And that gives me a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Am I missing a path? 1, 4. Yes, 1, 4, 7. 1, 2, 3, 4, 7. This path I was missing. So when you write it all down, you get 13 paths again. Again, it's one. One is not in the middle. In this case, it's over here in the corner, and still the same thing. Still the same thing happens. We still have the same number of paths. So the question is, what is going on here and here at the same time? Why is this different from this? What makes it different? What is the differences? So these edges obviously matter. Every pair of neighbors, their edges matter. Somehow we're getting now 13. We're getting these pairs of edges. Maybe let's look at them. I invite you here, pause for 10 minutes, think about this. And the thing is, well, if you think about the edges, what you're having is these new paths. So you have this, the 1, okay. You have this valley. And then if you think, for any two neighbors, say 9 and 6 are neighbors, there's a directionality, like I can go from 6 to a 9. And then I can look at neighbors of 6. I can go from 5 to 6. But if I keep looking at, say, now the neighbors of 5, I can say I'm going at neighbors where I'm going down. I can either go down at every single point, or I've reached a valley, and that's 1. So here it's, if I'm looking at two neighbors, I know that one of the paths will go from 6 to 9. I'm looking at two neighbors, 3 and 9, I go, one goes 3, 9, and ends. I look at 6 and 5, it goes 5, 6, and ends, right? This is why I can have these multiple paths along the way. But it seems to be here that every two neighbors I pick, there's only one path that ends with 4, 8, and that was over here. There's only one with 3, 4, only one with 1, 9, 1, 2, 2, 7, 3, 4, 4, 7, 3, 9, 3, 5, 5, 8, 5, 6, right? There's only one such path here for all of these. However, over here, it seems there's multiple paths that end in the same last two digits. And I invite you here, pause, try to find one. And here's one. So we have a 1, 2, 3, here a 4, 5 here, and a 4, 5 here. We have a 4, 5 twice. A path that's uphill ends with a 4, 5 twice. And let's see why that is happening. So we went 1, 2, 3, 4, 5. And then I went 1, 4, 5. Okay, so now the trouble is, once I go from 4 to 5, I have two ways to go back to a 1. But if I only have one way to go back to my 1, to my valley, I should only have one path that ends with a 4, 5. So you see this thing, right? This is something we see from playing around with small cases. Now we're looking at, oh my God, this is what matters here. There's only one path that ends in a 3, 7. That is the thing we notice. The thing that's different between this and this and this is how many endings there is. For here, there's two paths that end in an 8, 9. There's 1, 8, 9, and 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's the difference. And so that's what motivates us to look, okay, what if we had, for every two neighbors, there's one of them is bigger, and we had one valley, and only one path from the valley ended in those two neighbors. well, then we'd have the same number of paths as we have neighbors plus the solved value. So we found here so far we're able to do that. So what we need to construct is a thing such that we can have these 2 times n minus 1 plus 1 paths, but to do that we need to make it so that we can't have 2 of them, 2 paths that are uphill that end in the same 2 things. And how do we get to those 2? From the same valley, how do we get to those 2? Well, if this was, say, 1 path, yada, 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 and now it goes to those 2, say A, B, and this is our valley, then there must have been another path from the valley that goes somewhere. It could be the same at most places, but at some point it combines into each other. Which means what? I invite you here, pause for 15 minutes and try to push the problem further. And now here's the next step. And what we have is, okay, this thing we're thinking about is really just saying, if I'm going to have, okay, I'm going to have like A and B, right? I'm going to finish at that from this valley, yada, 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 go to A and B. And then I have another path from the valley that goes yada, yada, and then maybe goes over here and then goes into A and B. What does this realistically mean? Like, what is this something that we can really measure very well? And the thing is, well, this thing happens. There's this like circle, right? There's a cycle, a circle of these paths that they meet up again, right? In those examples where we had the minimum number, they never met up again. So what we cannot have is we can't have, if we have a cell, A, B, say B plus A, and we have, say B plus A plus, say B plus A, say here we have C. Actually, let's just say it goes to B. And say that B is bigger than A and B is bigger than C. So we have these directionalities. And now we can't have B and its neighbor, there's another neighbor, say D. We can't have this happen, right? We can't have B goes to D. So what does that mean for us? It means if we get to this cell that has at least 2 of them going into it, then that cell has to be the end. All of its neighbors have to be less than it. So we cannot have this sort of situation where if we have 2 cells that are going into one, then we can't have this go out to some other cell. And if we're able to construct this, then we actually have this for every 2 edges. There's exactly 1 path that ends with those 2, the cells that make that edge, right? And I'm saying edge here, like this shared edge between the shared edge. Okay, so now let us first, actually write that down, prove that. Why? This is 2 points, right? Seeing this with the edges thing, going in and out, that's 2 points, along with a minimum. So the minimum here is, we say, okay, if we have a board that's n times n, there are a total, and we connect these, squares, these n squares with their neighbors. We draw an edge between them, 1, 1, 1, 1, 1, 1, 1, and we draw them in such a way that the edges are directed. They are edges that go from smaller to bigger one. Now, if we just reverse order, if we always go from the bigger one to the smallest edge, we are at some point going to reach a place where we cannot go any lower, right? And if we're at that place, that means that every neighbor to up, down, left, right, wherever we can, it has at least 2 neighbors. Every neighbor is bigger than it. In other words, it's a valley. So for every pair of edges, we will be able to find a path that ends in them for any 2 pair of edges, right? Start from the valley and it can go to those 2 edges. But we start from the 2 edges and went down and down and down, and then we found our valley. Okay, so that is 1 point, which means now we have how many edges do we have? Well, there are n cells, there are n minus 1. There are n minus 1 edges between the cells in a row, a total of n rows, so a total of n times n minus 1 row-wise edges, and n times n minus 1 column-wise edges. And of course, there's the one valley thing with one more edge. So we get this, 1 point. Again, 29, I said this in problem number 3, 29 points with silver. You want to try to get that 1 point. And even if you don't think this works, even if you don't think about these fours and whatnot, these forks, you still have, you should still write down a banal estimate, right? This is not a strong estimate at all. Like, this is taking something, the smallest thing, like it has to be that. It feels wrong that it's a solution. We might be wrong. But so far, if you think about it, if I don't have this thing happening at any point, that means that every path, and if I only have one valley, that means that every path to any edge is unique, right? If I have a sink like this, it means every path to it is unique. There's nothing stopping it, right? There's no place, if I'm going back, I'm forced to go back only down one route for every edge. I have just one path that I can go back to my valley. So it seems plausible. Now, of course, there might be difficulties even constructing that. So what do we really need in our construction, or are we thinking about it in this way? Well, we're going to need to have some way, okay, say for 4, we're going to start from A1, and then we need to make these edges in such a way that we don't have anything that will produce 2 edges. So for example, if we go from 1, 2, 3, 4, 5, here I can have something big. Forget about it. But just 3 and 5 can sink into that. That's okay. Let me use my smaller numbers for the other things. So I can put a 6 here. I can leave this wide open. But if I leave that wide open, then if I go here, I need to take all of these into consideration. What if I go 7, 8, and if I go 9? Okay, I've still not created any doubles. So I go this way, 9, and then say, I don't want to have any doubles here either. I want to somehow be able to close up these edges. Let me try a different approach. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11, 12. Okay, but if I make a 12, then this creates 2 wedges over here. And if I was to put something else over here, is going to be less than a 2, 3, or a 4, right? So can I actually construct this for a 4? What is this thing I need to construct? And trying to characterize what that thing is 3 points. Now, take that in consideration, those 3 points, along with 3 points from problem number 3 that I talked about in the previous video. That gives you a gold medal if everything else was okay. So, and there are people who had 2 points in problem number 3. It's more plausible to have 2 points as opposed to 3. And 4 points here. You can get 4 points by doing this thing I'm asking you to do right now and constructing this for infinitely many n. That's 4 points. And there are, I think, 3 or 4 contestants from, I think, Australia, India, and Iran who have had that sequence 772, 774 and got a gold medal. So it's not implausible, it happens. Learn from those people. And now try to construct this for 4. Look at what you need and then try to construct it for 5, for 6. What are you trying to construct? I really urge you to play with this and try to see if you can reach this, make it a minimum. Come on, go ahead and do it. And now let me clear up the board with the construction. And now what you see, once you do some construction with some fiddling around, you notice a couple of things. One is, it really matters, this path of numbers 1 through some 12 really matters, but it doesn't matter which order they're in. The only thing that really matters for us for these numbers is now here, everything will sync, right? Everything here that's not part of this will go and sync, right? It won't go anywhere else. Here we have this and this. And it really only matters that these numbers are in such a way that you don't have two paths going over here, that they are in a sequence, and it doesn't have to start from one. It goes like 1, 2, 3. Both of these paths work out. What matters for us is that there's no forking that's going on 2 in, 1 out. That's the thing that matters, but the actual ordering does not. So we need to construct this in such a way, this big sequence of one-way orders, right? This thing from the valley. We can even think of this as a, it starts from the 1. That's maybe, the root of all the valleys. And then we have a structure that is, it's actually by definition, it's a tree. Like this whole chain, call it, or a tree. Like this is by definition a tree because no two numbers here are there's no cycle here. And there's just one less edge than there are numbers in here. So it's by definition a tree. Everything is fully connected. There's one less edge than there are numbers, so a tree. And they all go to the root 1. And I think that's what really matters. What matters is not where 1 is located over here. What matters is that we have this way to make it all go back to 1. And same here. And what matters also is that the rest of these squares, the other squares that are not part of this chain, are what? That they're isolated from one another. That no two squares that are outside of this are neighbors. Otherwise we would have that fork thing happen. But here, for numbers that are on the chain, they can only go down one direction, say from 1 to 2, from 2 to 3, from 3 to 14, 14 here. Like none of them are neighbors that are on the tree. Like they can have the exact same number of neighbors. Like this is the tree. And now I can input all of these other numbers in these positions. All the paths will sync into them, and that will create our problem. To just state that this is not what we're trying to construct, this tree chain-like structure, that with this no forks deal, 3 points, and now let's go ahead and try to construct it. So we have this sort of thing. We're looking at how this tree really looks, right? That is what we care about. This is for 4, like the equivalent tree structure. So if this is a thing we care about, now let us try to construct that for 6. And that's what our problem is boiled down to. If we cannot construct it for 6, mind you, if we can't construct it, say not for 6, but for some n, but we have a nice pattern that, could work in many instances, say just a pattern of just all of them one next to another, maybe fill up a row, and then say under what circumstances, like I like, for example, there's this, edges going between themselves. Like maybe is there a way for me to go 1, 2, combine these edges, then have this one be taken, but say, can I do a similar thing like here, like these crosses, for what n can I just create these cross sort of thing that looks nice-ish, but this is sort of messing me up. Like I like the fact that they're crossing the ones that I need, like this one, these two go out, this one goes out, so maybe there's a way to cross those things, but even if you can just construct this for that kind of end, that's also 4 points. You're already on gold. Maybe you need a 7 for this problem, but go ahead, try to construct that. That is what you're playing around with now. So let us continue onwards. How do we construct that? Well, let me clear this part up with the numbers, because the numbers really don't matter anymore. What matters is how we construct this chain. So let us delete that and remind ourselves of how we've constructed chain for, say, 4, 5, 3, 2, and 1. And how we construct this is really a matter of, preference. I'd like to go down that idea to see, like, how can I have this sort of, crossing structure? This is like a ladder of a sort from here to here, here to here, here to here. How can I create that in general? So I'll need these, crosses. Say I have a cross, I'll have this situation. And on the other side, I'll have this situation, like that. There's a cross over here. These are independent lines. Okay, now there must be a way for me to connect them. I can't have any two neighbors be here, so I'll need to connect them over down here. Maybe this is my connection. Then I can do and extend the same one over here. Have the same thing, and now, okay, now I have these crosses for some n. Right, this is now our tree. So this handles multiples of 3, I want to say. Like if I add 3 more, like I can just do the same thing that I had here. Just do that. And I've added 3 more. And I can continue to do this indefinitely down here. So now I have every multiple of 3 constructed. just like that. Every multiple of 3 is constructed. I just need to determine what this structure really is, how I'm going to call it, but we're pretty much done with multiples of 3 at this point. Again, formalization is important. It's not going to be trivial whatsoever. No, like we're going to need to define this term here for 6, right? And then just copy paste it over here for as long as we need it. This part isn't too difficult, but the difficult part is what? Constructing it for non-multiples of 3. How are we going to do that? Again, I invite you, like maybe, is there a way for us to reuse this structure for that? Maybe I can cut off this part and the down part. Yeah, I can actually do that. That gives me multiples of 3 minus 1. But you try to formalize this. Take 5, 10, 15 minutes, play with this, and tell me what you get. Come on, do it, and put it down in the comments below if you find a different sort of construction. I would really, really like to know. And now let us continue onwards. So we have this sort of construction. I can justify it for n is equal to 6k or 6k plus 3. Right, this is what I'll be doing is I'll say, let's call this 1, 1, all the way till, so 6k, this is 3, 6, 9, so this will be like 12 or 6k. So if n is equal to, like what is happening here? Like I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. The real difference is between the 2 and the 5. So in the first row, so if n is equal to 3 times t, then I color the first row and what's it called? 1 and r, where r isn't congruent to 5 modulo 6. That is what I'll do in the first row. And then in the second row, what I'll do, I'll cover 2 and say p, where p is what? P is not 1, 3 modulo 6. That's the only thing that really matters to me, where p isn't congruent to 1 or 3 modulo 6. And everything else I cover. And now I say, obviously this path is connected, yada yada. And now, because these are like, I have my gaps here, but then I have my 2 and p covering that. And I have gaps here, so there's nothing, this path is a tree if I start from 1, work my way upwards. So I'm kind of coloring these. And then I take every, for every 2 here, every 2 or 5. So if I'll take 6k plus 2, right? So for 6k plus 2, I'm going to go to that column. 6k plus 2. Actually, this whole column I will just color I and 6k plus 2. And I and 6k plus... I'll color I and 6 and just 3k plus 2 for all I that are greater than 2, right? I start off... I already colored the 2, so now I'll just color all of these columns. And then what I'm left with is I need to define a coloring for the neighbors. So I'll need to color in these two columns. So that is going to be 6k plus 1, 6k plus 3. And I'll color them at either odd or even intervals. So here it seems I'll color them for the odd numbers for 2s plus 1, 2s plus 1 and that. These I'm also coloring, getting part of my tree. And here it's the evens ones that I'm coloring. Okay, so this takes care of n is equal to both 6, n is 0 modulo 3. However, if I have say 10 of these, say I have 11 of these, let's start off more simpler. Like the ends, I can just cut off. This is the great thing about this coloring. I can just cut off the ends and say, forget about them, who cares? And the rest, I can then think about, okay, well, actually, I can just take off the leftmost column or the rightmost column, depending if it's 1 or 2 modulo. So yeah, if it's just if it's 2 modulo 6, if it's 2 modulo 3, I'll just cut off the first column and the bottommost row. Otherwise, I'll cut off this column. And I'll just cut off 2 bottom rows and a left and a right column. And with that, the problem is solved. That's the construction. That is the motivation. And that is how we solved it. Like how we solved the problem now is if we have this type of construction, then we just put numbers 1 through some t, like whatever t is, how many numbers we have, in these, such that they're consecutive, such that they go 1, 2, that they form really a tree such that there's only one value. That's what matters. And we can do that if we put them one after the other. If I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, I just need to go one after the other so that they're in sequence. That's what matters, that I'm putting them at their neighbors they're all in the sequence and their neighbors. That's what matters. Like I could even start, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? Go off like that. The only thing that matters is one value, una value. So with that, I put all the other big numbers in these gaps, and I would need to prove mathematically that these gaps actually do exist. And you want me to do that? Well, sure. How we do that is we can just characterize what these gaps are. So these things are obvious gaps. I think at this point it's a problem number 6 at the IMO. If you've characterized it like that, gave a couple of examples. I really don't think there's much that they could say like, oh, you weren't specific enough. You had the right idea and you had the proof that these are gaps are really just busy work, it seems to me. I don't know of a super duper quick way to do that. Well, say we can characterize them, I think is the best thing. So these are numbers. So for 6, we can go okay, we have it for 6k, we have it for 3 times k, and then we're going to go down to, we have then plus 3, we're going to go down to, right? We're going to have for multiples of 3, and they're going to go down 1 or 2. So how we prove that this is connected is, if all the numbers in all of these triplets are connected, and that this is how they are connected in these columns. They're connected on the first row. And we need to also specify this, that there is a connection here. We need to just prove. We need to say a word about this being connected. I just write, it's obvious they're connected. And from there on, we say, okay, these are the gaps on column 1. And then I can, I know what the other gaps are. I know the gaps are, say, 6k plus 1, 6k plus 3, and the even ones, 2s and 2s. And now I say, okay, the numbers up and down are already in the trees, so we're good. So they're smaller than them. And the numbers left and so the numbers, so for this one, the number to the right, actually let's go here. So for this one, the number to the right is part of this tree. The number to the left is part of the other tree coloring. So the 2s, which I did not write down, the 2s and 6k plus 4, 6k plus 6, and 2s. The one that's to the left of this one is already colored, 6k plus 6. The one that's to the left of this one is colored. The one that's to the right is 6k plus 4. It's colored. It's colored, it's part of the tree. I'm using these terms interchangeably. And then we'd say, that means all of these have, just like one sink. There's only one value, and we can populate that the way we've described. And with that, the problem is really solved for all n. Like, sure, we need to maybe say a bit more about what happens when I actually cut them off. Like the fact that I can cut off the bottom to the bottom, anything at least except these two rows, except the first 2 rows that I can cut off and still have a valid construction is really not an issue. We just need to, say something about these 2 boundaries, that it's okay to cut them off. And with that, the problem is solved. We can also characterize this for if you have time, you're like on problem number 6, like mind you, if you're in the IMO, you're on problem number 6, you solve this. You could do a power move and just, walk out of the exam hall early, or you could spend time going through 6k plus 1, plus 2, plus 3, plus 4, plus 5, and plus 6, and try to actually construct that and write out a couple of examples for k is 1 and 2, or n is 1 through 12. And that would solve your problem. Just doing that, which is kind of wild, but hey, that would work. That would work. And if you think about it, like, this is a cool problem. In my point of view, a very, very, very cool problem, because it involves a construction like this, which is difficult to come by. Mind you, this maybe sounds like it's a bit easy to come by. It's not. But the main thing to take away from here, for me, is that these smaller cases helped us see what the problem was. We had a hypothesis, it's one value, we're good. And then, no. There's variance even if you have one value. And you see that while playing with 3. Hypothesis fails. Okay, what is the thing that gives me 22 on one hand and 13 on the other? Okay, there's these edges. It only ends in each pair of edges once. Okay, 13, and it also makes sense that there are 12 edges. There's the one that's always going to be there no matter what, so it's not implausible. And here I have it ends twice in one edge. And then the question is, okay, what makes it end in the same edge twice? Well, 2 going in and 1 going out, this sort of fork, okay. And then 2 points so far. And then you get, okay, so what I need to construct is, so I don't have these forks. How do I do that? Well, I'm going to start from 1, and 1 is going to be connected, going to go out with all of its neighbors. So wherever they're going, they can't go, like this one cannot go here, because then they might both go into the next one. Unless it's a sink. Let me look at the non-sinks, where they are going, because they are the things that matter to me. The non-sinks. And the non-sinks say they need to be part of this thing, and they can't be neighbors, because if they're neighbors, then there's 2 going out, 2 going towards 1. So they can't be neighbors, and with that, you have a construct, what you need to construct. With that, you have 3 points, and then It's a matter of you coming up with that construction, which is you coming up through play. You're trying to find something that's generalizable, at least some end that you can deal with. Okay, trying this for 4, 5, 6, maybe try even till 9, and then you come, oh wait, I can actually repeat this pattern often, right? I see it for 4, it's actually for 5. I see it come up, and I'm like, oh, this was very nice. How did you, cancel each one out? And for 6, it's even more visible when you try to construct this for 6. You even see the pattern up closer, because what you'll get is it's very easy to extend this for 6. Just, do this and do this, and you've extended it for 6 now, right? Just by that, you've extended it. So you think, okay, maybe there is something to this. I can keep on extending it. Could I extend it to a 7? Well, not quite on this side. I would need something different perhaps. So how am I going to create that, right? How do I create this for 7? And then I actually think about it, it's not at all trivial, because you're like, oh my God, I have to find another pattern. But you write out the one for 6, for multiples of 6 and multiples of 3. You write it down, and you see, oh, wait a second, this multiple, actually, if I just remove these, I have, like, for example, if I have 1 to 9, if I just remove these, well, now I have 2 through 8. That gives me 1 through 7. That's my 7. That's my construction for 7. I have these 2 walls at the end. And from there, I get these spikes. And that finishes up our problem. And as always, thanks for problem solving.